Hello, myself Professor Devidas Dige from Matosri College of Engineering and Research Center. I welcome you all for the course of Electromagnetics. The objective of the course are to introduce the basic mathematical concepts related to the electromagnetic vector fields. Another objective is to impart the knowledge on the concepts of electrostatics, electric field, electric potential, electric energy density, and the applications. Third objective is again to impart the knowledge on the concepts of magnetostatics, magnetic field intensity, magnetic flux density, scalar and vector magnetic potential, and the applications. Next course objective is to impart the knowledge on the concepts of Faraday's law, then induced EMF, and the Maxwell's equation. Thereafter, again we need to impart the concepts of time varying magnetic field, that is electromagnetic waves, and the transmission lines. Now, this entire course is divided into 6 units. The unit 1 consists of electrostatics, that is electrostatics 1, which deals with the first basic coordinate systems required to study the electromagnetics. Then the vector field operations, curl, gradient, and divergence, which are used in electromagnetics. Then we discuss the Coulomb's law and its applications to find out electric field due to the various charge distribution. Then the Gauss law and its applications. Then the electric potential and the uniform and non-uniform field concepts. Unit 2 is the extension of electrostatics again. Unit 2 is electrostatics 2, which deals with dielectric, polarization of the dielectric, then the dielectric strength, the nature of electric field in the various dielectrics, boundary conditions, after the boundary conditions, the energy density, Poisson's and Laplace equations, then the capacitance, various types of capacitance and the parameters related to the capacitance and the combination of capacitance. So first unit deals with the electrostatics, it is a static electric field. The third unit consists of magnetostatics. There is a static or a stationary magnetic field or a steady magnetic field. It deals with the Biot-Savart's law and its applications. Again, further we will study the Ampere-Circuital law and its applications. Then the vector magnetic potentials. Then the magnetic flux density, scalar magnetic boundary conditions, and the density, energy density. The fourth unit, now your static field part is over. Now fourth unit deals with electrodynamic fields. Those are varying with respect to, or variation with respect to times are provided over there. So it deals with the Faraday's law, then translational and motional electromagnetic force, there is EMF, electromotive force, then the displacement current, then the time varying Maxwell's equation in point form as well as in integral form, power consideration in time varying fields, and the Poynting vectors, and the retarded magnetic potentials. This is the end of your fourth unit. Now in the fifth unit, it's related to the transmission lines. It deals with the various parameters related to the transmission line, various characteristics of the transmission line, where different ways to terminate the transmission line, or the various ways by which you are connecting the transmission lines, and the various ways to connect the input and the output, and the problem related to the same. So you need to solve the problem theoretically, on paper, as well as by using the Smith chart. So at the end of the unit, you are going to discuss the problem based on the transmission line by using the Smith chart. Now the last unit is related to the uniform plane wave, which deals with the Maxwell's equation in phasor form. Then you are going to find out the wave equations for the time varying fields. Use these wave equations then deal with them or rearrange them, then find out the depth of penetration, nature of these fields in various materials like in dielectric or in a perfect conductor or in a lossy conductor, perfect conductor and the actual conductors, practical conductors, how it goes on behaving and how it behaves with the ideal dielectric and a practical dielectrics. Then after that, again in that same unit deals with the reflection of the electromagnetic waves. So it goes to the reflection along the plane surface or oblique surface, then the reflection coefficient, transmission coefficient and the Snell's law. So this is the entire subject electro or the entire course of electrostatics. Now we'll start with the first one, entire subject of electromagnetics. Now first we'll start with the first unit, that is electrostatics. So while studying the electrostatics, before starting with the Coulomb's law, every one of you must know about the coordinate systems. So coordinate systems are required while studying the electromagnetic. Why? Because without coordinate system you won't able to understand the concept of waves properly, or we won't able to deal with them mathematically. Until now you might have studied only a rectangular coordinate system or a Cartesian coordinate system, where there are the three coordinates x, y, z are there from the origin, three mutually perpendicular coordinate axes are there, and then you are expressing the point anywhere inside the space by using the three coordinates x, y and z. Those might be positive or negative. Like such, there are 13 different coordinate systems. These are coordinate systems, 13 different coordinate systems are there. Out of that, 3 you are going to discuss. Those are the Cartesian coordinate system, that is a rectangular coordinate system which is already known to us. Then the circular cylindrical coordinate system, and the third one is the spherical coordinate system. So what is meant by the coordinate system? Coordinate systems are just an idea to express the location of the point. The location of the point inside the space remain fixed. Only the way in which you are specifying that location goes on varying. Now why we need this different coordinate system if already a location is given by one coordinate system? Now these three different coordinate systems are utilized to make the calculations or computations as easier as possible. In support of it, I will give an example. Suppose you are interested to find out perimeter of a circle, or you are going to integrate on the perimeter of a circle. In terms of Cartesian coordinate system, we need to deal with the equation of a circle, that is x square plus y square is equal to r square, and we need to integrate along x as well as y axis. But if you are going to use the circular cylindrical coordinate system, that integration quite becomes simple and we need to integrate with only one parameter. Similarly is for the various different types of objects, like a surface of a sphere. If you are doing the surface integration, we need to integrate along x, y as well as z coordinate axis, and if you are using the Cartesian coordinate system everywhere, then the problem becomes quite complex and the solution is time consuming. So to make your solution simpler, these different coordinate systems are used, and coordinate systems are just idea to express the location of the point. The location of the point remains same, only we are specifying it by different ways. So first we will start with the Cartesian coordinate system, which is already you have studied. So we will go through the first Cartesian coordinate system, and then sequentially we will discuss the circular cylindrical coordinate system and the spherical coordinate system. Coordinate systems are three different coordinate systems we are going to discuss. The first one is the Cartesian, or the, we can say, rectangular coordinate system. Second one we are going to discuss the circular cylindrical coordinate system, and the third one is spherical coordinate system. So first we will start with the Cartesian coordinate system, where you might have already studied it right from number of years, right from your schooling you are studying this Cartesian or rectangular coordinate system. So all the coordinate system we are going to discuss over here are in terms of three-dimensional coordinate system we need to discuss. So in Cartesian or rectangular coordinate system, these are of two types, right hand side or the left hand side coordinate system. So generally we are preferring the right hand side Cartesian coordinate system. What is meant by right hand side? In case of right hand side, if or as in Cartesian coordinate system, it consists of the three axes x, y and z, which are mutually perpendicular to each other. These are the three axes x, y and z. This whatever we have drawn, this coordinate system, the origin, and from origin there are three coordinate system x, y and z. All three are mutually perpendicular to each other. In right hand side Cartesian coordinate system, if you are moving a right hand screw from x to y, it moves or it progresses in the upward or along the z axis. In case of left hand side, if you are moving from x to y, the screw will goes on moving in the negative x direction. So most of the screw are based on the right hand screw rules or right hand side systems. So in case of the Cartesian coordinate system, we are going to express the location or a point P inside the space. Now for all the coordinate system, the origin is always remains the same. For all the three systems, origin is same. Only these are the different ways to express the location of the point. So in case of Cartesian coordinate system, we are able to express the point P as a intersection of the three planes. As the point is located in terms of x coordinate, y coordinate and a z coordinate, a point P is located inside the space having three coordinates x, y and z. That is the distance x from the origin, point is at a distance x from the origin, or y is the distance with respect to the y axis from the origin, and z is the distance from the point P with respect to origin, from the origin with respect to the z axis. So this x, y and z are the movements of the point P. As you are moving towards the point P, these are the movements along the x, y and z axis. So to locate the point P, we need to draw the intersection of the three planes. First draw a plane x equals to constant, then y equals to constant, and respectively a z equals to constant. So to avoid the confusion, just I have drawn the three figure over here. So you may found this figure where a point P is located at one of the corner of this cuboid. Okay, and one corner carries the origin and point may be located at any other corner, which consists of the three axes x, the three coordinates x, y and z, where point P is located by the intersection of the three planes. This particular plane is x equals to constant, this particular plane is y equal to constant, and this upward or top one is the z equals to constant, and the point P is located at x, y and z. Same thing is shown over here. This is the x coordinate. There is distance as you are moving from origin to the point P. With respect to x, you are moving by a distance x. With respect to the y axis, you are moving by the distance y. With respect to the z axis, you are moving by a distance z. So these are the x, y and z coordinate. These are the distances measured with respect to x, y and z axis. These are the coordinates. Now when your point is located and the vector is drawn from origin to the point P, this particular vector is called as a position vector. This position vector indicates the position of the point P from the origin, and the position vector is given as, now with respect to these three axes, first of all we need to discuss before specifying the position vector, let's suppose there are the unit vectors are called as the base vectors. Unit vector along the x-axis is given as ax. Ax stands for unit vector along the x-axis. In some books, the unit vector might be expressed by x cap also. I am going to use a with suffix x bar, that is unit vector along the x-axis, unit vector along the y-axis, unit vector along z-axis. So unit vector won't have it will have a magnitude 1. So basically unit vector is used to indicate the direction, and for all the axes you are able to draw a unit vector, and the unit vector is directed The unit vector is directed in the direction of increasing coordinate. So ax जो होगा, ax is unit vector along x axis. It is directed in the direction of increasing x coordinate. It is in increasing y direction, and here ay z is in a direction where y coordinate increases. Now we will express the position vector, and the position vector is given as summation of the three components, that is the component along x axis, component along y axis, component along z axis. That means this vector is specified as a addition of three vectors. This is the vector along the x direction, vector along y direction, vector along z direction. The vector along x direction is, let's suppose this is the vector a, then it is the ax, ax, ay, ay, and az, az. So vector is represented by the addition of the three components. Similarly, for this point P, the position vector is specified as the unit vectors are given. Unit vector indicate the only direction, and the position vector of the point P is given as x, ax bar plus y, ay bar plus z, az bar, because your end point is x, y, z and the starting point is origin. Similarly, we are able to have a distance vector also between the 2 points. In case of distance vector, vector is drawn between the 2 points A and B. Suppose the point A is at a location x1, y1, z1. Point B is at a location x2, y2, z2. Okay, then the distance vector between the points A and B is given as, so it is the vector from point A to point B. So always it is to be find out by using difference between the coordinates of end point to the starting point. So it is x2 minus x1 ax, y2 minus y1 into ay bar plus z2 minus z1 az bar. This is how we are representing the position vector in Cartesian coordinate system. Now in the same question, suppose a point P over here, and move the point P by a differential amount. When you are saying the differential amount, differential means what? A very, very small, where the change in coordinate cannot be measured. Then it is called as a differential movement. So when you are moving by a differential amount from the point P, so x coordinate is increased or x coordinate is varied from x to x plus dx. Y coordinate is varied by the differential amount y plus dy. Z is also varied by z plus dz. So point P, you are moving x coordinate by differential amount, y coordinate by differential amount, z coordinate by differential amount, and it gives us a differential volume. Okay, this differential volume will have the x variation, y variation and z variation. So it looks like a cuboid. This differential volume will have 6 surfaces enclosing a volume, and it is having the variation of the length along the x axis, y axis and z axis. Now as you are having the differential volume where the x variation is dx, y variation is dy, z variation is dz, and for this differential volume the differential length is specified as, let's suppose for this Cartesian coordinate system, this is how we are able to express the differential volume first. The differential volume is the small differential variation along the x, y and your z axis, that is the height. Okay, this is the dz variation, dx variation, dy variation. Now in this case, when you are moving along the x axis, these are the different lengths and it having the surfaces. This face surface will have the z variation and the y variation. So this surface area is dy, surface area will be dx. This variation is x, so it is dx dz. This particular top surface is dx dy, bottom surface is also dx dy. So these are the different surfaces. Now we'll express them in mathematical form. For this differential volume, it is having the length variation. So along the one edge you are varying either x axis or y axis or z axis. Means the variations are dx, dy or dz. So in this case, Here we are varying the x, y and z. So differential distance, if you are moving from one point to the diagonally opposite point, that time we need to vary all the three axes, that is x, y as well as z. That's why a differential length is given as dl is dx ax. In this case they are written as x cap, because the ax or x cap both are used to represent a unit vector, that is ax bar or the x cap. So these are the unit vectors. So it is dx ax plus dy ay plus dz az is the differential length in case of Cartesian coordinate system. Now in this case, at a time you might be varied either only x axis, y axis, z axis, or all the combination of the d axis. Means suppose along this line you are varying only x, along this line only y, along this line only z. But when you are moving along the diagonal, you might be varying 2 or 3 coordinates. That's why this is the differential length. Now this differential volume have the 6 faces, that's why it carries the 6 surfaces. And differential length, 6 surfaces are specified either dx dy, dx dz or dy dz. But differential surface is a vector, and the vector should have the magnitude as well as direction. So for these differential surfaces we should specify the direction. While specifying the direction of the surface is always in the outward direction. That's why for this side the surface, this direction is outward, which is along x axis. That's why the surface is dy dz ax bar. In opposite side, on opposite side, whatever the face is there, it's again the surface area is similar, dy dz, but the direction is minus x, because that time it is outward, is along the negative x direction. Similarly, top surface dx dy direction az, bottom surface will have minus az. Similarly, on the right hand side and the left hand side, the right hand side surface dx dz direction ay, and on the left hand side it will be dx dz minus ay. So these are the surfaces. 3 different differential surfaces are there. Only the directions are either plus or minus. That depends in which direction the perpendicular is. And when you are varying these 3 coordinates, it encloses the volume, and it specifies the differential volume as variation of all the 3 coordinates, because the volume of this cuboid is length into height into width. So it is the differential volume dv is dx into dy into dz. So these are the different differential length, differential surfaces and the differential volumes in case of Cartesian coordinate system. Is the circular cylindrical coordinate system. In case of circular cylindrical coordinate system, point is located on the surface of a cylinder. So to locate the point on the surface of cylinder, we need to specify the 3 parameters. Then radius of cylinder, second one is the height of cylinder, and the third one is angle made by the radius of cylinder with a axis parallel to the x-axis, or in 2-dimensional system it is the angle made by radius of the cylinder with the positive x-axis. That's why that angle vary from 0 to 360 degree. And intersection of planes corresponding to the radius of cylinder constant, height of cylinder constant, that is z constant, and the third one is the angle phi constant, will be a location of the point. So first plane is the cylinder, second plane is the plane with a constant z, and the third plane is the half plane, which is including the z axis perpendicular to the xy plane, makes an angle phi with the positive x axis. And in case of a circular cylindrical coordinate system, you are going to express the point P on the surface of a circular cylinder. So for circular cylindrical coordinate system, we need to locate the point on the surface of cylinder. We need to express the location in terms of radius of cylinder. Then we need to specify the height of the cylinder at which the point is located, and the angle of the point with respect to a fixed position which is parallel to the x-axis. By specifying these three parameters, we are able to express the point on the surface of a cylinder. So let I have seen it in this particular figure. It is being shown how a point is point is located. So point is nothing but intersection of the three different surfaces. First is a constant radius cylinder. This is how it is being shown. Second one is the z equals to constant, height is constant, a infinite plane is there. This infinite plane is cutting the cylinder. Initially the location of the point, when radius is specified, location of the point is entire surface of the cylinder. But after specifying a plane z equals to constant, now the point lies at the intersection of the two surfaces, and now point lies on the circle, which is the intersection of the two surfaces. Now the next one, we are going to specify an angle phi. It is an angle phi is angle measured by a half plane, which is half plane is passing from z axis onwards, and this half plane is perpendicular to xy plane. Okay, this plane is perpendicular to the xy plane, and this half plane makes an angle along the x axis. This particular angle is next one is specified. That phi constant, that angle is called as this particular angle is a phi, and this angle phi constant is again a half plane. Now as you are after intersection of the two planes, probable location is on the surface of circle, and by using the third plane phi equal to constant, all the three planes are going to intersect only at a single point, and that is nothing but the location of the point. This is where the point is being located. Okay, so the location of the point is present over here, which is the intersection of all the three planes. Rho constant, radius constant, radius of the cylinder is constant, then your z is constant, height is cylinder is constant, and then the angle measured by the half plane with respect to the x axis is maintained constant. Now as we are specifying the location of the point by using this cylindrical coordinate system, to express the point we need to specify, already you have come across, we need to specify the radius of cylinder. The radius of cylinder, now already the origin of all the coordinate system is fixed. So these are your x, y and z axis. Now to locate this point on the surface of cylinder, what we need to specify? The radius of cylinder. Circular cylinder is having an axis along the z axis, and with respect to z axis we need to specify the radius. That's why this radius is varying from 0 to infinity, because it is from z axis onwards. This radius we need to specify. Generally it is specified as rho. In certain books it is also written as r, but just to avoid the confusion between the circular, cylindrical and spherical coordinates, I am going to utilize it as a rho. So rho is the radius of cylinder, and which is varying from 0 to the infinity. It can extend up to infinity. Second parameter, to locate the point we need to specify the height at which the point is located, that is z. The z coordinate is similar to the coordinate lies in the Cartesian coordinate system, which is varying right from minus infinity to the plus infinity. So z coordinate is varying from minus infinity to the plus infinity. Now the third one, we are going to specify an angle phi. Angle phi is angle made by the half plane. This angle made by this half plane with respect to the x-axis is an angle phi. As you are going to specify this angle with respect to the positive x-axis, angle phi will vary from 0 to 2 pi. It can vary from 0 to 2 pi. So angle phi is vary from 0 to 2 pi, and that's where the point P is located in terms of coordinate rho, phi and z. This is why you are writing the rho, phi and z. It is having a certain meaning behind it, because you are knowing that in Cartesian coordinate system we are always writing the coordinates in the sequence x, then y and then z. So in the same way we need to write down rho, phi and z. What is the logic behind it? Because in case of I think you are aware of the cross product of the vectors. So when you are doing ax cross ay, it is always found to be az. That's why you are writing the coordinates as x, y and z, and you are able to draw a right clockwise circular, right clockwise variations over here. So if you are doing x cross y, okay, if you are doing x cross y, it will be plus az. So if you are moving in the direction of arrow for the cross product, the cross product is positive. If you are moving in the direction of arrow for the cross product is positive, and that's why the order is x, y, z. Similarly, over here is rho, phi and z. If you are having rho cross phi, it is plus az, and z, if phi cross az is arrow, or vice versa. And that's why these coordinates are given in the sequential form rho, phi and z. Now, as we are specifying the location of the point in terms of a circular cylindrical coordinate system, this is how the point is located on the surface of cylinder. In this case, this r is nothing but the rho is the radius of cylinder, rho. Then sometimes it's specified as rho, sometimes it is r. The point lies on the surface of cylinder, who is having a radius r, angle phi and height z. Now for this point P, we need to specify the unit vectors. Unit vectors along the radius of cylinder, unit vector along the height of cylinder, that is along the z, and unit vector along the angle phi. So in this case, the unit vector in the direction of radius is given as AR cap, AR bar. This unit vector, now I have specified it over here. This is the unit vector along the AR cap, or it is also arrow cap. It is shown in the outward direction. Why? Because when you are moving outward, the radius of cylinder goes on, increases. Always unit vector lies along the increasing coordinates. From this point on P, the z coordinate varies in the upward direction. That's why this unit vector along the z axis is AZ bar. Similarly, when you are moving towards this y axis, your phi angle increases. That's why this A phi is along this direction. This A phi is tangential to the cylinder, whereas AZ is also tangential to the cylinder, but AR is perpendicular to the cylinder. Now what is an interesting thing is over here, in Cartesian coordinate system, the direction AX, AY, AZ always remains constant. But in case of circular cylindrical coordinate system, the direction of A phi, AR goes on varying, and OZ only remains constant. I will give an example. Suppose if your point P is at this location, then at this point, the new values of AR, A phi, and these are the AZ. Okay, only AZ remains same, but AR is changing direction, A phi is also changing the direction, because AR is always, or arrow is always perpendicular to the surface of cylinder, and A phi is always tangential to the surface of cylinder. So we are having the three unit vectors along the radius rho, then phi and the z. Now in similar to the Cartesian coordinate system, in cylindrical coordinate system also, we are able to specify the position of the point in terms of a position vector, and position of the point is given as PR or P rho, A rho, then P phi, A phi, and PZ, AZ. What is P rho? Is the rho component of the vector. P phi is the phi component of the vector, and PZ is the Z component of the vector. Okay. Now suppose we will consider a differential volume in a cylindrical coordinate system. So let's suppose a point P is at a location rho, phi and Z, and now vary the coordinates of the point P by the differential amount. Means, I will show it on the same figure over here. Now for this case, suppose if you are varying the consider the differential volume, vary your radius, vary your angle phi, and vary Z. So it gives us the space, specifically a object of this particular type. It is not an exactly a cuboid, because it will have a various curved faces it will have. Just I will show it one on a figure. Okay. So over here you may see this differential volume in case of a cylindrical coordinate system. What the differential volume is? Along the radius of cylinder, radius is varied, as well as your angle phi is varied, and the angle height z is varied. Now whatever the differential volume you are getting, it will have the three different lengths associated with it. The first length, as we are varying the coordinate r by a differential amount, so coordinate r is varied by a small differential amount, that is r is varied by 1 minute. So r is varied, or the radius rho is varied by a differential amount d rho, or we can call it as a dr. So this is what the radius variations dr or d rho. Then you are varying the z coordinate by a small amount dz. This is what the height is, the dz variations. Now this particular curved surface is being obtained by varying an angle phi. But angle phi is not directly you are getting in terms of a length. So in this case, when you are varying the angle phi in terms of arc upon radius, angle is arc upon radius. This is the angle phi variation. This length we need to find out. This is the radius r. So as your angle phi is arc upon radius, by using the definition of angle in terms of radians, this length is nothing but r d phi. This is the length you are getting. It is r d phi. So these are the three different lengths lies with it: r d phi, dz, and the d rho or dr. This dr, dz, and r d phi. These are the three different lengths associated with the differential volume. Now these three lengths will have the 6 different surfaces. That's why this front surface, this particular front surface, your radius is constant, you are varying angle phi and z. That's why the two lengths you are multiplying for the surface area are r d phi and dz. This what is r d phi? This is a change in length in terms of change in length in terms of change in angle. So it is r d phi dz. Surface area is r d phi dz, and it is directed along direction of the surface, perpendicular to the surface, and in the outward direction. The outward direction is along the radius. That's why the surface area is r d phi dz in a direction ar. Similarly, top surface, you are varying the length r d phi, and the next one is dr. So it is r dr into r d phi. So the net is r dr d phi. Direction upward, that is az. For downward it is minus az. इसी तरह जैसे front surface ar, back surface will have minus ar. Now the left and right surface. For the right hand surface, the two lengths you are multiplying are dz and dr. So it is dr dz, direction a phi. Here the direction is minus a phi, because in this direction phi increases, in this direction phi decreases. So these are the different differential lengths you are having for it. So differential length and differential surfaces. So the differential length is combination of variation of all the three coordinates. So differential length is dr ar, r d phi a phi, dz az, because three lengths are dz, dr, and r d phi. Similarly, it will have the three different surfaces, and the opposite surface will have the direction minus ar, minus a phi, minus az. So the front surface r d phi dz, then the top surface is r dr d phi, and the right hand side surface is dr dz a phi. Now when you are multiplying all the three coordinates, it gives the particular volume of this particular entire volume, and this differential volume is nothing but multiplication of three lengths dr, r d phi, and dz. So then these three lengths are multiplied and you are getting a differential volume. This is the differential volume. These are the differential surfaces ds, and this is what the differential length in case of circular cylindrical coordinate system. Now once you are knowing this basic idea about the coordinate system, now we will go for the conversion from cylindrical to the Cartesian or Cartesian to the cylindrical coordinate system, because coordinate system are only idea to express the location of the point, and you may specify the location by different ways. So that's why we must know how to get, because same point, if it is in Cartesian coordinate system, it will have the coordinates x, y, z. If the same point is expressed in cylindrical coordinate system, the point will have the coordinates r, rho, r, phi and z. So now I will draw the coordinate system. These are the three coordinates x, y and z in Cartesian coordinate system, and the point P is located over here. The point P will have the height z, then x intercept and the y intercepts. So this is the y coordinate, this is the x coordinate, and this one is the location of the point P. Now when the same point P is expressed in terms of, so point P will have the coordinates x, y and z in Cartesian coordinate system. Now the same point is expressed, suppose in a cylindrical coordinate system, it will have the coordinates r, phi and z. So this is nothing but the radius of cylinder, which is perpendicular to the z axis and moving towards the point P. And now this is the height z, which is same as the earlier one, and this is nothing but an angle phi measured with respect to positive x axis. Now in this case, as this is the radius r, this is again the radius r. So this side is x, this one side is x, so you are getting a right angle triangle over here, whose two sides are x and y. This angle is phi, and this one is your radius of the cylinder r, or the rho we can say. Okay. Now by using the right angle triangle, what you are saying, cos phi is side length by hypotenuse. Sin phi is front side, that is y, divided by hypotenuse, that is r. Now by using this, by using this trigonometric relations, now value of x is r cos phi, value of y is r sin phi. Now x and y is known. What is your z? Z coordinate is same as the z coordinate used in the Cartesian coordinate system. That's why if the point is having the coordinate r, phi and z, we are able to find out x, y and z in Cartesian coordinate system. X is where x is r cos phi, y is r sin phi, and z is same as the initial one. Now suppose, rather than in cylindrical coordinate system, if the point is located in terms of Cartesian coordinate system, and we need to find out r, phi and z. Okay. Now we'll again come back towards this particular figure over here. Now as we need to specify the location in terms of r, phi and z, just to avoid the confusion, let me consider this particular figure. This point P, this is your r, this angle is phi, this height is z, and these are the x and y intercepts. These are the values of y and x. This is again the radius. Now from this figure, what we can say, again this for this right angle triangle over here, consider this right angle triangle, which again obtained on the bottom side. This is your x, this one is y and this one is r, this angle is phi. Now to obtain the r, what is your r? The hypotenuse square is first side square plus second side square. That's why hypotenuse, that is the radius r, is square root of x square plus y square. So you are able to obtain the radius of cylinder. Now once your radius of cylinder is known to us, next thing is we need to find out phi. What is your phi over here? From this figure, we are able to express cos phi or sin phi or tan phi. But if you are going to use cos phi or sin phi, it involves radius, which is not known to us. So we will find out the tan phi. So what is the tan phi for right angle triangle? Tan phi is sin phi by cos phi, which is front side by side length. So it is y by x. So phi is tan inverse of y by x. So if you are knowing x, y, z coordinates, we are able to find out an angle phi. Phi is tan inverse of y by x. Now the one interesting point over here is, this phi is tan inverse of y by x. So depending on the values of y and x, the tan phi
y by x will vary. Y by x can vary from minus infinity to plus infinity. That is, only possibilities are there. If the x is 0, it is infinite. If y is negative or x is negative, net value is negative. If both are positive, then it is positive. So it varies from minus infinity to plus infinity, and that time the angle phi will vary from minus pi by 2 to plus pi by 2. But what is the actual variations of an angle phi? But practically it is found that angle phi is varied from 0 to 2 pi. That's why one correction is over here. When you are saying phi is tan inverse of y by x, it is to be utilized when only x is positive or negative. लेकिन y हमेशा क्या चाहिए? Y always must be positive. Y must be always, y may be positive or negative. 1 minute, okay. Y can be positive or negative, and x must be always positive. That time we need to use tan inverse of y by x, because that time your might lies in the first quadrant or in fourth quadrant where the angle is 0 to 90 or minus 90. Okay. But when the x value is negative, when x is negative, that time angle phi is pi plus tan inverse of y by x. So pi action. Now the z coordinate in Cartesian and your circular cylindrical coordinate systems are again exactly same. That's why the value remains same as it is. Now is how at the end I will summarize how to convert it. If you are having the x, y and z coordinate, then r is square root of x square plus y square. Then angle phi is tan inverse of y by x. Optional is, if x is negative, then we go for pi plus tan inverse of y by x. Z coordinate is same as z. This is an interconversion between the coordinate system. But if you are having the cylindrical coordinate system components r phi z, then find out x as r cos phi, y is r sin phi, and the z coordinate remains as it is. So this is the conversion between the coordinate systems. Next is the spherical coordinate system. In case of a spherical coordinate system, the point is located on the surface of sphere. When you are locating the point on the surface of a sphere, what we need to specify? The radius of sphere and the two angles. One is the angle in 2 dimension and second one is the angle in 3 dimension. So first angle is similar to the angle used in circular cylindrical coordinate system. It is the angle made by the half plane parallel to the xy plane along with the positive x-axis. And the second angle is the angle of a cone, and the cone is having apex at the origin, and the cone is measured, angle of the cone is measured with respect to positive z-axis. So these 3 planes, now there are with these 3 parameters we are having the 3 different planes. The radius equals to constant plane is a sphere, and the 2 parameters are angle theta and phi. Angle theta equal to constant is a cone, and the third one is the angle phi constant is a half plane including the z-axis perpendicular to the xy plane. These 3 planes intersect at a single point, that is nothing but the location of a point. Specified. Now the probable location of the point is on entire surface of sphere. Now to restrict the location, we need to specify the 2 angles. One is the angle, azimuth angle, and the second one is one is the angle phi, which is similar to the angle used in the circular cylindrical coordinate system, and third one is the another angle theta. That is the angle theta is the angle made by the cone, or it is the angle made by the 3-dimensional angle made along with the positive z-axis. Now as we are specifying the point is located on the surface of a sphere, or point is given by intersection of the 3 planes. One is sphere. Okay, in spherical coordinate system, point is located by the intersection of the three surfaces. First is the sphere, second one is a phi equal to constant half plane, and the third one is the cone with respect to the origin. Okay, this cone, this particular half plane, and the sphere. Now when you are saying the sphere and a cone, the intersection is nothing but found a circle over here, and when consider the intersection of the third plane, all these 3 points, 3 planes are going to meet at a single point, that is the location of the point P in a spherical coordinate system. Now to specify the location of the point, we need to specify the 3 parameters of the 3 planes. The first parameter of the sphere is its radius. Okay, second parameter of the phi equal to constant plane is phi, similar to the circular cylindrical coordinate system, and third is the angle theta. Theta is the angle of a cone. Okay, so this angle theta we need to specify to specify the cone, and now the intersection of the 3 planes will be a location of the point. Same thing is given over here, or it is specified as a intersection of the 3 points. Okay, this is your sphere, phi equal to constant, and a conical. These three surfaces meets at the single point, that is the location of the point. So these are the 3 different constant surfaces with respect to the Cartesian coordinate system. The first one, radius constant, then phi constant, and then theta constant. So 3 coordinates we need to specify: r, phi, and r theta and phi. Now the sequence is different. Phi is not considered. R theta is over here. Sorry. Okay, 1 minute. Like this, we need to specify. This is the radius r. This one is an angle theta, and this is an angle phi, for the similar to the cylindrical coordinate system. But when you are specifying these coordinates, we need to maintain the order. It is slightly different. That's why we are specifying the point P in terms of 3 coordinates: r, theta, and phi. This sequence is again based on the certain assumptions, but prior to that, just we will discuss about the unit vectors, and then we'll go for the differential volume. So first we will discuss about the unit vectors in a spherical coordinate system. And when you are saying the unit vectors in a spherical coordinate system, for the spherical coordinate system we need to specify. Now don't consider the remaining values in this particular figure, only concentrate along the unit vectors. Just I will discuss it on this figure, and then we will go further to the diagram. So in this particular case, at this point P, we need to specify the 3 unit vectors along the 3 different coordinates. These 3 unit vectors in the direction of increasing coordinate. So from the point P, there are unit vectors along the radius, unit vector along the angle theta, and unit vector along the angle phi. The unit vector along the radius is perpendicular to the surface of sphere. Unit vector along the phi is perpendicular to the phi equal to constant plane, and unit vector if theta is perpendicular to the conical surface, but this perpendicular is in a outward direction, because in outward direction the radius, or I can say the cone, angle of the cone increases. That's why these are the unit vectors along radius, along phi, and along theta. R, theta, and phi, these are the 3 unit vectors. These 3 unit vectors again goes on varying depending on the location. If the point lies somewhere on the sphere, AR is different, A theta is different, A phi is again changing. So all the 3 unit vectors goes on varying their location based on the position of the point. Now we are having the 3 unit vectors along AR, A theta, and A phi. Now these are the 3 unit vectors along the 3 axes which are varying, and these unit vectors are in the direction of increasing coordinates. That's why from the point P, if you consider the with respect to the Cartesian coordinate system x, y and z, suppose this is the location of the point P, this is AR direction, then this one is an A theta, and this is the direction of A phi you are getting. Now once the unit vectors are known in the different direction, now you are specifying the sequence r, theta and phi. Why? Because AR, A theta and A phi. Again, if you are moving in the direction of arrow, the cross product is positive, else it will be negative. That is, AR cross A theta will be plus A phi cross AR will be plus A theta, or A theta cross A phi will be plus AR. If you are moving in the opposite to the arrow, then it will be negative. Now we will move further and we will consider the differential volume or differential element in a spherical coordinate system. Now in a spherical coordinate system, for differential element vary the coordinates of point P by the differential amount, that is r is varied from r plus dr, then theta is varied from theta plus d theta, and phi is varying from phi plus d phi. When you are varying this angle by the differential amount, okay, it constitutes a differential volume, or a very small volume where the change in coordinate cannot be detected over here. Just I will show you in terms of a figure over here. Okay, this is how we are considering the differential volume. Okay, this is nothing but a simple differential volume where your radius is varied, then your angle theta is varied, that is a conical angle, and angle phi is varied. Now we are varying these three parameters r, theta and phi. This volume looks like such. This is an entire volume. Okay, how it looks like. This space is this one. Okay, it is exactly matching over here. This is the top surface over here. Okay, and these are the different in this entire differential surface you are having. Now for this differential surface, okay, we'll again show the different figure for it. This is what the differential surface looks like. Now for this differential surface, it will differential volume. It consists of the 6 surfaces and the 3 different variations of length. So the first variation of length, when you are moving upward, you are varying the radius. This is the variation of length. First variation of length is dr. Okay. Now when you are varying an angle phi, that time your length variation are different from the angle, because when you are varying the angle, the variation of length depends on the radius, because angle is arc upon radius, and as we are interested in the arc is nothing but angle into radius. So in this particular case over here, first we are varying the theta, that time this again the radius r, and this change in length for the theta is r d theta. Why? Because d theta is this length is angle d theta is arc upon radius, that is r. Arc is nothing but the length, and this arc is found to be, what is the arc? This arc is found to be r d theta. Okay, that's why this change in length is r d theta. But when you are varying an angle phi, when you are varying an angle phi, that time your radius is somewhat different, which is not the radius of the sphere. That time the radius is r sine theta. We need to represent this radius r, and it is represented as r sine theta, and that's why this angle in terms of arc into radius is arc is nothing but the radius into angle is r sine theta, and angle is d phi. That's why there are 3 different length, dr, r d theta, and r sine theta d phi. 3 different length variations are being observed in case of spherical coordinate system. Now when they are varying the length, it will have the surfaces, so it will as well as have the volume. So in this case the different surfaces are, okay, just I will show the surfaces over here, okay, and the radius. Okay, in this case, this is how we are getting the different elements. So it is r sine theta d phi. Only here rather than lowercase they are shown in uppercase, and this one is r d theta. These are the another length, and the third length is dr. That's why volume is multiplication of the all the three lengths. First length is dr, second length is volume is the multiplication of the three lengths. dv is equals to dr into r d theta r sine theta d phi. When you are multiplying them together, it is r square sine theta dr d theta d phi is the differential volume. Similarly, we are able to have the differential surfaces. On this top surface, radius remains constant. Only we are varying the remaining two components, that is r d theta and r sine theta d phi. That time the front surface is r square sine theta d theta d phi. Direction is plus ar. Now we consider the differential surfaces over here. So when you are having the three different lengths are there. So the length variations are dr, r d theta, r sine theta d phi. When you are varying any two coordinates, it will give us the differential surfaces. First one is r dr d theta. Direction is remaining coordinate, that is a phi. Plus or minus, that depends where the surface is located. Second one, remaining these two coordinates variations, r square sine theta d theta d phi. This is the differential surface. Now the direction is ar. Another differential surface, first and last coordinate we need to vary. r sine theta dr d phi, and the direction is in direction a theta. So these are the three differential surfaces, and the differential volume is multiplication of the three coordinate system. It is r square sine theta dr d theta d phi, and the last one is the differential length. And differential length is nothing but the combination of all the three variations, that is dr ar plus r d theta a theta plus r sine theta d phi a phi. So these are the differential length, differential surfaces, and differential volumes in case of spherical coordinate systems. Now the next one, relationship between the Cartesian and the spherical coordinate system. So you consider the relationship interconversion between coordinates between spherical to the Cartesian coordinate system. So when you are saying the Cartesian and the spherical coordinate system, a point might be located in r theta phi or as well as x, y and z component, because just coordinate system are idea to express the location of the point. So in this particular case, I will show one example over here. Now in this case, a point P is already located in a Cartesian coordinate system. The point P is having the coordinate x, y and z, where this is your x component, y component and the height is z. Now for this particular point, if it is expressed in terms of a spherical coordinate system, where this r, theta and phi are located, that time this is nothing but this is the radius r, okay, and this particular angle is phi and this particular angle is theta, okay. Now in this case, by using this particular figure, okay, this is nothing but the diagonal of a diagonal element. So this is your z, and this one is square root of, as it is a right angle triangle, x and y are, these are the two sides. So this particular diagonal is square root of x square plus y square, and this value is z. These are the two sides of the right angle triangle, and this is nothing but a diagonal, okay. This is nothing but the diagonal. This is this particular. That's why these are the two sides. First side square plus second side square is the hypotenuse square, and that's why it is found to be square root of x square plus y square plus z square. So it is nothing but found to be a radius. So radius of cylinder is square root of x square plus y square plus z square. Now your angle phi is similar to the cylindrical coordinate system. Tan phi is front side by side length, that's why it is tan inverse of y by x, okay. tan inverse of y by x, and the r, phi and theta. So now we need to find out an angle theta properly. So what is your angle theta over here? To find out your angle theta, okay, for this case, this is your we can say radius, or sorry, this is your height z, this is a right angle triangle, and what is your cos theta? Cos theta is side length by hypotenuse. So here cos theta is z by r. Z square root of r is x square plus y square plus z square. Now by using this concept further over here, your theta is expressed as cos inverse of z divided by square root of x square plus y square plus z square. This is how you are able to express the angle theta. Now before considering these expressions over here, we'll consider the possible variation of the components in spherical coordinate system. So in case of a spherical coordinate system, you are using the three coordinates r, theta and phi. As you are using the r, theta and phi components, here r can vary from 0 to infinity because the radius of sphere cannot be negative. So it is varied from 0 to infinity. Phi is the angle which already you have discussed, is varying from 0 to 2 pi. Now what is your angle theta? It is the angle of a cone. Angle of a cone, it is measured with respect to the positive z axis. Now we are varying this cone. This cone is varied like such with different angles. At the end, for 90 it will be a plane surface, and for beyond 90 the cone is being inverted. Okay, the cone is being inverted beyond 90. So it will be a conical surfaces for all the angles except 90. At 90, theta equals to constant is a plane surface. So what it indicates? The theta is varying from 0 to 180, or we may say it is varying from minus 90 to plus 90, minus pi by 2 to the plus pi by 2, because in the lower side the angle is considered as negative and it is positive on the upper side. Just to avoid the confusion, rather than negative, better to express it in terms of 0 to pi. Okay, so this one will consider the angle 0, and over as it goes on moving downward along the negative axis, the angle is 180, and here the angle is 0, here the angle is 90, which is pi by 2. Okay, so these are the three variations you are getting. So angle r, theta and phi are varied as r is varying from 0 to infinity, theta is varied from 0 to pi, and phi is varied from 0 to 2 pi. Now further we will go through the conversion of coordinate system. Just now we have discussed how to obtain the spherical coordinates in terms of the Cartesian coordinates. Okay, just I will summarize them over here as r is square root of x square plus y square plus z square, then phi is tan inverse of y by x. Now again the rule applied is similar one. If x is negative, that time we need to add 180 to it, it is pi plus tan inverse of y by x, and theta is cos inverse of z divided by square root of x square plus y square plus z square. Now we'll consider the conversion from Cartesian coordinate system xyz to, already we have considered xyz. Now we'll find out from r, theta and phi. We will find out in the reverse direction. Already we have discussed Cartesian to the spherical. Now we will discuss spherical to the Cartesian. That is r, theta and phi is known to us, and try to obtain the Cartesian coordinates x, y and z. Now for this case, we will again go through one already available figure with me. So for this, from this figure what we can see, this is the radius, angle phi, and this one is angle theta. Same point if it is expressed in terms of Cartesian coordinate system, okay, then in terms of Cartesian coordinate system, this is your height, that is nothing but the z. This side is distance y, this side is in distance x, y and z, r, theta and phi. Now we will try to obtain x in terms of r, y in terms of and z in terms of r. So to find out your r, this is your r, so this side is ये नीचे वाली side, bottom side, diagonal. This is r sin theta. Once the hypotenuse r sin theta, what is your sin phi? Front side by hypotenuse. So cos phi is side length by hypotenuse, and that's why by using this, what we can say, this r, this here we are getting r sin theta. Now, okay, just 1 minute. Once it is r sin theta, what is sin phi? Sin phi is y divided by r sin theta. Sin phi is y divided by r sin theta. So, just 1 minute. Okay? So here sin phi. Now we will try to obtain these Cartesian coordinate in terms of a spherical coordinates. Okay. So in this case, this is your r, and this particular diagonal on the lower side in terms of theta, it is r sin theta. Once it is known as r sin theta, we will try to obtain the remaining coordinates over here. Once this diagonal is r sin theta, now you are having the right angle triangle over here. This side is r sin theta, this angle is phi, this is 90, this one is x and this one is y. Now for this right angle triangle, what we can say, your sin phi is front side by hypotenuse, that is r sin theta. Cos phi is side length divided by hypotenuse, r sin theta. And by using this, what we can say, x is r sin theta cos phi. Then what is your y? Y is r sin theta sin phi. Once your x and y is known, what is your z? Now again over here, okay, this is your r, this is your angle phi, this is the right angle triangle over here. What is cos phi? Side length by hypotenuse, this is z by r. As cos phi is z by r, z is r cos theta. Okay, so these are how you are able to obtain the Cartesian coordinates from the spherical coordinates. So this is the conversion between the coordinate system spherical to the Cartesian coordinate systems.